In ellipsoid method, we use ellipses to divide the finite space into parts and look for satisfying assignment and finding a smaller and smaller parts. To understand that, we need to understand how to represent ellipses, how to compute ellipses from ellipses, and cut them and splice them and join them, whatever you want to do with the ellipses. We need to have some understanding how to handle ellipses in mathematical form. Okay, so before understanding ellipses, we need to know positive definite matrices, and that actually defines an ellipse. What is a positive definite matrix? Which is all eigenvalues are positive. The following statements are equivalent about positive definite matrix. So how do we understand positive definite matrix? If it's a positive definite matrix, then we can represent it as a multiplication of a non-singular matrix B, and its transpose multiplied with itself, then it gives you this matrix D. If you take any vector and dx, and it will give you positive greater than 0. And how do we prove that? So how do we prove that? If all eigenvalues are positive, then it's a diagonalizable, and if we diagonalize, then we obtain d equals to pt d prime p. Since d prime is a diagonal matrix, what you can do is, and it will consist of the eigenvalues of the matrix, and since all of them are positive, then what we know is that you can actually break it down into two parts, which is basically square root of each eigenvalue, and you can write the b as bt times d double prime. Therefore we have the second state. We can easily prove from 2 to 3 is that if x is not equals to 0, then we can write d as a btb, so you get x transpose bt bx, and then you get xb transpose bx, and then x goes here actually, and then you can say that just a squares is greater than 0. Now we have to look for the 3 implies the first condition, and we will leave that as an exercise for all. So how these positive definite matrices are useful to understand ellipse? What you can do, you can take a point and a positive definite matrix, and you can define an ellipse. So an ellipse is an area which is basic set of points, so that x minus z, and if you multiply x minus z to d inverse both directions, and then you will get, and say less than equal to 1, then that those points are called ellipses, and they look like ellipses. Okay, and z is the center of the ellipse, and d defines the directions and the length of axes. Okay, well, let's look at an example. Okay? If let's suppose you're thinking about 2D ball, so at the origin, so that the center is at 0, 0, and the d matrix is I. Okay? So it defines the matrix, this circle, this interior space, and you can see that the natural fits our intuition of the ball, a unit ball. So let's look at a real ellipse, how the real ellipse would look like in this notation. So this is your origin, 0, 0 still, and ellipse is stretched in one dimension, let's suppose in this dimension, and then what you do in that dimension we write 4, and then y dimension you say is 1. Okay, so you can if you write in the form of expanded form of the ellipse, then you can write this way. Now let's shift our ellipse into x direction, then we can change the origin, and we obtain the symbol shifted ellipse. We can also rotate our ellipse, and if you rotate our ellipse, our ellipse will be represented like this, and we can write down our ellipse in the following. Now remember that what we were talking about, that we wanted to have a space which is defined by ellipses, and then we get a smaller ellipses that we can find the satisfying assignment. So how do we split and splice ellipse? What we can do is that we can evolve, and a line goes through an origin, right? And then we say there's a half of the circle, and this part let's approximate using a ellipse, and this is probably a small space, and this is how I'm going to get a smaller and smaller uh, ellipses. So let's see how can we can make sense out of it. So let's suppose A is a direction which from origin A, and in this direction you have a plane and you want to cut this ellipse circle into half, and you have to find the smallest ellipse that contains this space. And if you do some mathematics, what you need to do is basically to find a point, center point. Let's say you call this as D. You say this is the smaller length is 1 minus D, and you can say that this is the point should intersect with position as 0 comma 1. And if you just put this constraint in your formula, you will find some constraints, some formula which represents the volume in terms of D, and then you try to find when the volume is minimum in terms of D, and then you do that, solve that problem, then you will find this ellipse, which will be the smallest ellipse that can contain this half circle. Now, what is the volume of this new small half circle? And if you estimate that you say that in one x dimension it shrunk by n divided by n plus 1, in all other dimension, in this case we were looking at the n was 2, and we look at the higher dimensions, then all other n minus 1 axes it will expanded by this much. So what do? You put them together, and this much volume change has occurred. Now if you simplify this, you will find that this formula is less than e to the power minus 1 to n plus 2. So every time you do this, you get exponentially smaller ball. We will use this fact to prove the polynomial size of our algorithm. So you can generalize this idea. Now you can we are earlier cutting a ball, you can also cut ellipse, and in arbitrary direction. Well, D defines the scaling and the rotation of the ellipse. You can just use the D to go back to the circle space, and then they're cutting, computing your approximate ellipse, and then bring it back. And if you do that, you will obtain this formula, and which can be easily checked out if you just do this linear transformation and send it back. So if I will use this notation. If you have a ellipse centered at position D, and then the ellipse is defined by this positive definite matrix D, and you want to cut this ellipse into half in the direction A, and then you try to find the smallest ellipse that contains this, then you find this ellipse. Okay. It looks very scary at front, but it is doing very usual method operations of linear transformations, and you get this formula back. So not too complex to say.